with the second component. Now I know that U1 consists of two components, x and y, or as I've written here, U1, U12. Start to use this formula and they make the substitution. So it's going to be U12, U12. Consider U1 sub 2 equal to positive 1. So the vector that we are talking about is 1 and 1. And if you remark the algebraic multiplicity, so the algebraic multiplicity of lambda 1 is equal to 1. And the geometric multiplicity of this eigenspace is also consists from one vector, so both of them equal to each other. Now I have a first vector, U1, which is simply 1 and 1. If I want this vector, okay, I'm not gonna go more than this, but I will redo all the steps once more, getting U2, which in the eigenvector corresponds to lambda equal to -2. So once more, similar manner, nothing new. This is U2, which corresponds to lambda, and in this case, it's equal to -2. This is exactly what's happening here. I've tried to solve this one, getting lambda equal to -2. So once more, move with me step by step. So now the matrix that we are talking about, it's gonna be -1, negative over 1 minus 2. Then I will have positive 1 equals 0. For the second row, I will have positive 1, -1 minus 2, and it's equal to 0. But remark that we are doing a mistake in here, because we take 1 minus lambda, so it's a -1 minus of a -2, which is positive. And also -1, which is minus a -2, which come up to positive value. And for that case, you will find your matrix adjusting very well, having 1, 1, and 0, and for the second row, it's going to also 1, 1, and 0. And as I told you previously, at this step, you should have either two identical rows or one of them is having an inverse, has a simple relation with this other row. Now, all I have to do is to try to get it as close as possible to a reduced echelon form. So I would multiply the first row by -1, adding it on the last row. So it's going to be 0, 0, and 0. This is going to be 1, 1, and 0. This is going to be U2 first component, U2 second component. So simply trying to expand it once more to equations. So it's going to be U21 plus a U of 2 equal to 0. So which means that the second vector first component equal to the negative of the second vector second component. You are all set. Now I can say that the second eigenvector, which consists of two components, U21 and U22, simply can be changed into a negative of U2 and 2 and U2 and 2, replacing or considering this value equal to 1. So this span of this basis of this set of eigenvectors is going to be -1 and positive 1. The thing that I want you to remark is that the second eigenvector, which is -1 and 1, stand for lambda 2. Also, the algebraic and geometric multiplicities of these two vectors are the same. Another remark, for working with a symmetric matrix, having this issue, remark that U1 and U2 are orthogonal vectors. So if you got U1 dot U2, you will find the result equal to 0. And this is an inner product or a dot product. It's really very easy to check. All I have to do is to get the multiplication of the first two components. So 1 times -1 plus 1 times 1, okay, times 1, and the result will be 0, which means they are orthogonal in each other. So this implies that they are orthogonal. The second step is to get a normalized matrix, or trying to get unit vectors out of these vectors. How to get unit vectors out of these vectors? It's very, very simple. All I have to do is to divide each component of this vector or that vector on its magnitude. A magnitude of a vector is simply the square root of the sum of the square of its components. So simply, now I can get to the S matrix, which I will use to diagonalize this given matrix, which is going to be simply, I will say or indicate that it is S or U star as we did previously. I will take the first eigenvalue to be its first column, which is going to be 1 and 1. The second eigenvector, it's going to be its second column, so it's going to be -1 and the positive 1. I will divide the first column by its magnitude, so all of this will be divided by the square root of the first component square, 1 to the power of 2, plus the second component square, which is 1 to the power of 2, which means all of these elements will be divided by root 2. Similar manner, they could be different, but here it's a coincidence that they have the same. It's the square root of the first component to the power of 2, which is 1, plus square root to the, to the power 2 of the second component, which is 1. That will lead you with the S matrix on this form. It's going to be 1 over root 2, also 1 over root 2, then it's going to be -1 over a root over 2, 1 over root of a 2. This is the normalized or the orthogonal normalized model matrix, which is simply a matrix which having their columns orthogonal in each other. Once more, what do we mean about orthogonal? If you multiply the first two elements and the second two elements and adding them together, the result will be 0, which means these two vectors are perpendicular on each other. This matrix is orthogonal matrix, which means its transpose is its inverse. Now I can say that if I got S, which is 1 over, times A times S minus 1, let's put it this way, S minus 1 times A times S, I will have a diagonal matrix, okay, with the principal diagonal equal to the elements of the eigenvalues. So S minus 1 will be simply is S transpose. So it's gonna be 1 over root 2, -1 over root 2. For the column, it's gonna be 1 over root 2, 1 over root 2. If we multiply it by the A matrix, which is given -1, +1, 1 and the -1, then multiply it once more by this matrix, which is 1 over root 2, -1 over root 2, then 1 over root 2, 1 over root 2, the result will be simply a diagonal matrix. This matrix is going to be diagonal with the principal diagonal, the elements of the eigenvalue. So I have the eigenvalue 0 and the negative, so this number is going to be 0, that number will be a negative over 2, and the remaining will be zeros. Remark, this is lambda number 1, this is lambda 1, and that is lambda 2. So a diagonal matrix with its principal diagonal elements are the eigenvalues of your matrix. All of this is stated here. So now once more, the eigenspace or associated to lambda equal 1 is 1, 1. We already got that. The eigenspace corresponding to -2, which is 1 and -1. Exactly right, -1 and 1, it will be the same. Okay, remark that these two eigenvectors are orthogonal. Yes, 1 times 1 equal 1, 1 times -1, the addition of them equal to 0, so they are orthogonal in each other. Both the algebraic and the geometric multiplicities of this eigen problem is already equal to each other, I can get the diagonal matrix, which is the 0, 0, 0, negative 2. And this is by using the S matrix, which is 1, 1, 1, negative 1. But I did all of this. Also, I did the normalization of this matrix in order to get an orthonormalized matrix. All of this also is stated over here for everything. One example, the matrix of D is S. This is S minus 1 since it is an orthogonal matrix. Doing so, you will have your diagonal matrix. Note that there is not a unique way, because I have started this problem as Omar, considering lambda 1 equal to 0. If any one of you use lambda 1 equal to negative 2 and the lambda 2 equal to 0, you will have these two columns switched and it will correct itself by itself. And for the diagonal matrix, it's going to be negative 2, 0, 0, and 0. And this is what's stated here for you. And also, if you choose another values instead of depending on one, you will have the general form, so it's already correct. Also, for a problem like this, it's also a symmetric matrix, it's a 3 by 3 matrix. If I try to solve it in order to get the eigenvalues and the corresponding eigenvectors in a similar manner, it will be the same, exactly the same. So I'm getting the characteristic equation, which is going to be 3 minus lambda to the power of 2 times lambda. I believe the remaining will be zeros for all of them. So the characteristic equation for this problem, I will just outline something for you here, and I will continue because I have a lot of things that I want to tell you about or to go through it just in a second. Okay. Similar manner, guys, if I want to get the eigenvalues for this matrix, it's going to be also the same. It's really very simple. Here is your determinant equal to 0. I will have 3 minus lambda for the first element, 0 and the negative 3. I have 0. Don't forget negative lambda. Then I will have a 0. So this is 3 minus lambda equal to 0. Then I will have negative 3 also. Then a 0 as I leave. Then I will have 3 minus lambda. If you try to get the characteristic equation of this problem, it's gonna be 3 minus lambda times a negative of a lambda times 3 minus lambda, which equal to 0. And this will leave you with the following: having lambda minus 3 to the power of 2 times lambda equal to 0, which means you will have either lambda equal to 0 or lambda equal to positive 3 with a multiplicity of 2. So the algebraic multiplicity here is 2 and the algebraic multiplicity here is 1. This is for the algebraic multiplicities. I will try to get the geometric multiplicity relative to 3. I want to show it to you. Okay, so if I want to get the corresponding eigenvector corresponding to 3, all I have to do is once more do the same steps of trying to solve this system or this homogeneous system of equation A minus lambda of y times the vector that we are talking about, and it's equal to 0, trying to solve for the values of this eigenvector, which is while we use 3, we will have, okay, I will do it very, very slow. So it's going to be 3 minus 3, then I will have 0 and the negative 3 equal to 0. For the second row, it's going to be 0 minus of 3, okay, and the 0 equal to 0. For the last one, it's going to be negative 3, also 0, then a 0 equal to 0. Now, if I try to rearrange that stuff, it's going to lead to the following. Okay, step by step. This one is going to equal to 0, and then I will have 0 and 1 and 0. For the second row, it's gonna be 0, 1, 0, and 0. And for the last one, I will have, okay, if we divide on -3, so it's gonna be a 1, okay, 0, and 0, and it's equal to 0. So this is the matrix. Let me check again once more. So having lambda, so it's gonna be 3 minus 3, which is 0, 0. I will have -3 for the last one. And for this row, I will have 0, -3, and 0. For the last one, I will have -3, 0, and then 3 minus 3 as we spoke together. So this is mainly the final form, as I told you. Okay, so now for lambda equal to 0. Okay, times lambda equal to 0, we will have here just in a second. Okay, so this is gonna be lambda square minus first second times 2, which is gonna be minus 6 lambda plus 9, and all of this times lambda equal to 0, so lambda equal to 0. Then I will try to analyze this problem. So, those elements times each other, then minus, I will have 9. I'm sorry, I did a stupid mistake here while we were working together. So it's gonna be -3 minus lambda, lambda 3 minus lambda. Then I will have minus and -3 times -3 times negative lambda. So it's gonna be a negative times negative, so it's gonna be 9 of a lambda. So once you try to expand your problem, okay, let's do it this way, negative. So -3 times negative lambda times -3, it's gonna be 9 lambda with a negative sign. So it's gonna be a positive. So once more, you try to, just give me 1 second here. I believe I have a problem, okay? Just less than a second. I will do it really, very fast. And this is what I'm telling you. You will have to be really, very careful while you are solving these equations. So I will have here 9, which is 3 minus, okay, negative lambda of lambda minus 3 to the power of 2 plus a 9 of a lambda equals 0. Just trying to expand it. So you will have negative lambda times lambda square minus 6 of a lambda plus a 9, okay, and this is plus 9 lambda equals 0. Now here it goes. These two elements will cancel each other, so you will have negative lambda cubed, then plus 6 of lambda squared minus 9 over lambda plus 9 over lambda equal to 0. They will eat each other, taking lambda as a common, so you will have lambda squared, okay, taking lambda as a common, lambda squared, I'm sorry, as a common, so you will have lambda minus 6 equal to 0. So now you have lambda equal to 0 with multiplicity 2 and lambda equal to 6. These are the two values of lambda that we are talking about. Here we go. That's exactly right. 0, 4 with multiplicity 2. And here the algebraic multiplicity is equal to 1. What I want to show you is to try to solve for the part that I have an algebraic multiplicity equal to 2. I'm sorry for this typo, but as I told you, it's an algebra, so you have to really take a good care, as you can see. Okay, I will try to back once more to this system, and I will try to solve it, as I told you. So this is the matrix that I'm telling you about. So it's going to be 3 minus 0, 0, negative 3, and it's equal to 0. For the second row, it's going to be all zeros, as you can see. For the last one, it's going to be negative 3, 0, 3, and 0. So once you try to eliminate or to get to the reduced echelon form, I will divide on 1. So it's going to be 0, 1, 0, and negative 1 equal to 0. And the last row is going to be all zeros. I will make this, replace them. Also, I will multiply this row by 3 and add it on the last row, so I will have a form like this. So now I will try to expand it once more. Let me use x, y, and z to make things easier on you. So this is the x, y, and z standing for u11, u12, u13. If I try to expand it, you will have the following. That that it will lead to that x minus z equal to 0, which means x equal to z. So now once more, for the eigenvector corresponding to this matrix, which is x, y, and z, that's simply z, y, and z, which can be put on this form. If you read me, this is going to be z, 0, and z plus a 0, y, and 0, which also could be put on the form taking z as a common, so it's going to be 1, 0, and 1, and plus a y as a common, so you will have 0, 1, and 0. Remark that the span of this eigen vector, or the eigenspan, now it's going to be 1, 0, and 1, and for the other vector, which is 0, 1, and 0, 1, and 0, with a geometric multiplicity of 2. Remark that this is done for lambda equal to 0. So the geometric multiplicity having two vectors and the algebraic multiplicity to the power of 2, they are sharing the same multiplicity as I told you. And this is exactly here. For lambda equal to 0, I will have these two vectors which represent the span. At lambda equal to 6, I will have just only these vectors. The set of vectors are perpendicular on each other and they are linearly independent. So if I want to have the diagonalization of this matrix, it will be simply according to here, could be 0, 0, as you can see, 0, 0, and 6. And for the matrix that we are going to use, these are the two vectors, 1, 0, and 1, 0, 1, and 0. And this is the vector corresponds to lambda equal to 6. And this matrix also, I will do exactly the same, dividing the elements or normalizing it. Remark that all of these vectors are perpendicular to each other. If you multiply the first two vectors, the result will be 0. If you multiply the last two vectors, the result also will equal to 0. So it's exactly the same as we spoke together. Let me check, just a second. Okay, perfect. Very good. Okay, this is the transformation matrix that I told you about. Now, I will get back once more to the quadratic forms that we did go through it by the beginning of this part, once I told you about the quadratic forms. Before we go further, I will introduce the quadratic form, and also I would like to show you some of the properties, all the steps, everything that's done. Just the 5 minutes, we will go through all of these slides. Just in a second. Okay. I will get back also to this matrix. If I want to write the quadratic form according to what we said previously, any quadratic form in a 3D, in R3, should be in this form. A of an x squared plus b of a y squared plus c of z squared, and it is also plus d, or let's say 2d of xy to e times x and z plus a 2 of an f, y, and z, plus think of anything else you can put. So it's a g times x, h times y, let's say j times z, plus a w equal to 0. This is the general form of quadratics in 3D. If I want to write the corresponding symmetric matrix, let's say the quadratic form relative to this problem, it's gonna be, okay, it's gonna be 3 for x squared plus a 0 for y squared plus a 3 for a z squared. So I'm taking the elements of the principal diagonal as I told you. Then for x and y, it's gonna be 0. So this term is not gonna exist. For x and z, we have negative 3. So I will have here negative 6x and z, x times z. I don't have y and z. This is the second and third. It's equal to 0, so I don't have it. So plus some number in x, if exists, some number of y, another number in z, plus a number equal to 0. This is actually the quadratic form relative to the to this matrix that we are dealing with, which can be rewritten as the following: x, y, and z, which is time this matrix, which is 3, 0, and 3. For the xy element, it's gonna be zeros. For the xz, it's gonna be negative 3 and negative 3. For the yz, it's gonna be zeros. And this is also, it's gonna be x, y, and z. And this, all of this stands for the quadratic form that we are dealing with. Okay, blah, blah, blah. Okay, this is the quadratic form. All what said previously, it's already here. So a quadratic form, x1 up to xn, it's going to be on the general form, x11, x1 squared, 2 of x12 times x12, blah, blah, blah. So, which can be written as simple as this. This is the matrix x1, x2, x3, or x, y, and z. This is the matrix that symmetric matrix that we are dealing with. And this is x, y, and z, as you can see. Okay, this is a symmetric matrix, exactly like the ones in the beginning of our slides. Now, we will be talking about the vectors, which form the basis, and it is also normal, since you are talking about orthogonal matrices. The orthogonal matrices, okay, having the advantage of their transpose, their transpose will be their inverse. And also, this is how to diagonalize, how to get an eigen, a unit vector out of every vector. And this is what we did exactly after getting the eigenvectors, dividing each eigenvector on the on the square root of the sum of squares of its components. This is all written here, as you can see. These are the advantages of having the symmetric matrix. Okay, and with all of this, all eigenvalues of A are real. U1, U2 are eigenvectors of A associated with distinct eigenvalues. They are orthogonal, which means their multiplication equal to 0. Already checked that. There exists an orthogonal basis. This is the basis that I told you about, Rm, consisting of eigenvectors of A. A is diagonizable. I can get it simply by BT, B transpose A times B, and this is the inverse, actually. So it's exactly the similar formula that we spoke about previously. Orthogonal matrices B is invertible, and its inverse equal to the transpose, as I told you. This is stating how to change, the change in axes that we are talking about. Here is the definitions of a positive definite, positive semi-definite, and so on. I would prefer going through this slide on behalf of this slide, which states that I will have a positive definite if and only if all the eigenvalues of A are positive. I will have a positive semi-definite if all the eigenvalues are either positive or contain a 0. Same goes for negative definite. It will happen with all the eigenvalues equal to negative values, and it could be a semi-negative if one of them equal to 0 and the rest are negative values, and it will be indefinite if you have a max between positive eigenvalues and the negative eigenvalues. Here, find the eigenvalues of matrices can be difficult. The following theorems may help you out to know if it is a positive definite or a negative definite. I will go through them simply. All you have to do is to get the right matrix, the upper left matrix, which is A11. Then I will go through A11, A12, A12, and A22. So for example, if I have 3 by 3, this matrix should be positive definite, or the determinant of this matrix should exceed 0. The determinant of this matrix should exceed 0, and also the determinant of it should be exceed 0, or positive, which means, so it's going to be a positive definite. A definition for the definite, for the negative definite, to have one of them positive, the other is negative, and so on. This is in order not to go through getting the eigenvalues by solving the equations or the polynomials corresponding to them. Okay, very good. This is some forms, some shapes of the quadrant. So if I was in R1, so I have q of x, this is the quadratic form assigned to it, which is ax squared, which is going to be a parabola. It's going to be positive definite if it was positive, the a, and it will be looking up, it will be open up. And this is for the red, which is x squared. 2x squared will be closed a little bit around the y-axis, so it's going to be 2x squared, and both of them are positive definites. If this value is negative, so it's going to be on this shape, okay? So this is for negative x squared, and this is for negative 2x squared. As you remark, when we multiply by negative 2, then also the two wings of this quadratic function will be closer to the y matrix, as I told you, and this is our negative definite quadratic matrix. If we are talking in 3D, you will get stuck with the paraboloid family, and it's huge. So if you look at this one in 3D, which is x squared plus y squared, it's going to be the elliptic paraboloid, and since all these elements are positive, the coefficients, so it's a positive definite elliptic paraboloid, this is going to be the negative definite for an elliptic paraboloid. If we are talking about q in R3, which equal to x squared, so you will be talking about a shape like this, which is parabolic cylinder. It's called a parabolic cylinder, as you can see. This is also another shape from the parabolic cylinder if it was xq equal to y squared. One of them is about the x squared and the other about the y squared. You also have a parabolic cylinder with negative definite if you have the values or the coefficients in R3 in front of x squared and y squared equal to negative, as you can see. Also, you will have hyperbolic paraboloid, or what's called a saddle horse, and this matrix is indefinite quadratic form, and as you can see, one of the eigenvalues is positive and the other is negative. And by reaching this part, we come to the end of our session today. Thank you very much for attending. I hope you understand it. Please try to solve by your hand one of the eigenvalues and eigenvector problems that already exist in your work. Thank you very much. Appreciate it. I hope the best for you forever. Thank you very much. Good luck. I will continue next session, inshallah, solving some problems as I told you. Thank you very much and enjoy your day. Thank you. Bye.